Observations of a stellar explosion that refused to fade away have astronomers scratching their heads. What created the blast, and could it explain massive black holes? How do you make a big black hole? LIGO has witnessed 4 black hole collisions, the space-time upheaval revealed in an incongruous chirp of gravitational waves. The signals tell us that these black holes each had between 20 to more than 30 times the Sun's mass. So we know big black holes exist. Artist's impression of a supernova remnant. NASA ESAG. Bacon STSCI stars in our neighborhood aren't typically that massive, though, and even if they are initially, they lose a lot of mass prior to and during a supernova explosion. Now, astronomers have observed a strange new supernova that might mark the birth of just such a beast. But the cataclysmic event holds more questions than answers. It just keeps going and going. A typical supernova explosion goes something like this. Pressure loses its sparring match against gravity when the stellar core collapses into a neutron star, a black hole. But the anti-gravity forces have the final say. The collapse occurs so quickly that infouling layers of stellar material slam into each other, creating a reverse shock that sends much of the star flying outward. The expanding shells of ionized hydrogen glow for roughly 100 days before fading away. That's what IIRCAVI Las Cumbres Observatory and University of California, Santa Barbara and colleagues thought they were seeing when the Intermediate Palomar Transient Factory IPTF caught the explosion dubbed IPTF-14HLS. At 18th magnitude, it appeared to be an unremarkable core collapse supernova. But several months later, the star reenacted a certain Monty Python sketch. It refused to die. The star, or what was left of it, remained bright not for 3 months but for almost 2 years, radiating all the while at the same rate as 500 million suns. Even now, 3 years later, it's still going strong. What's more, it got even brighter at one point, and then again, altogether exhibiting 5 distinct peaks in luminosity when it should have been fading away. IPTF-14HLS grew bright and dim again at least 5 times over 2 years. This behavior has never been seen in previous supernovae, which typically remain bright for approximately 100 days and then fade. LCOS Wilkinson. A look back in history showed that this wasn't the star's first act of defiance. A possible outburst was recorded at IPTF-14HLS's position in the Palomar Sky Survey back in 1954. An image taken by the Palomar Observatory Sky Survey reveals a possible explosion in the year 1954 at the location of IPTF-14HLS left, not seen in a later image taken in 1993 right. Credit post LCOS Wilkinson. There are other oddities too. As it continued shining, the hydrogen gas maintained its temperature at a steady 6000 K. That makes sense if we're seeing the glow of expanding shells of ionized hydrogen. First we'd see the outer shell, then, as it expands, thins, and cools, we'd see through to the next glowing shell. But if that's the case, then the inner shell should be traveling at slower speed, and that's not the case here. Hydrogen gas, which started shooting out at 8,000 kilometers per second 18 million miles per hour, only slowed down to 6,000 kms 13 million miles per hour. The radius of the light-emitting region also appeared to stay constant, rather than expanding outward over time. An exotic explanation. Putting it all together, IIRCAVI and colleagues rule out most standard theoretical models for supernovae. The last one standing is one of the most exotic apparent instability supernova PISN. If a star is massive enough but not too massive, the incredible temperature and pressure of its core converts photons into particles, namely electrons and their antimatter partners, positrons. The resulting instabilities set off multiple supernova-like blasts, each ejecting tens of solar masses of gas. If the star's initial mass was just above 100 suns, it could have produced the multiple explosions astronomers witnessed from IPTF-14LHS. But these exotic supernovae have their share of problems. For one, we've never definitively detected one, though candidates have been suggested in the past, and the model could explain the most luminous supernova ever observed. The explosions also require massive stars not typical of our stellar neighborhood. These explosions were only expected to be seen in the early universe and should be extinct today, says co-author Andy Howell, also at LCO and University of California, Santa Barbara. This is like finding a dinosaur still alive today. If you found one, you would question whether it truly was a dinosaur. Even this exotic scenario might not even provide enough energy to explain what they witnessed, the researchers argue. Simple calculations show that the observations require 20 times more energy than a PISN could provide. But Stan Worsley, University of California, Santa Cruz, author of a perspective piece that accompanies the Nature article, notes that we don't understand pair instability supernovae well enough to invalidate the idea on this basis. A bigger problem may be the temperature. A pair instability supernova can't explain why the temperature would remain constant. As of now, Worsley writes, no detailed model has been published that can explain the observed emission and constant temperature of IPTF-14 LHS, let alone the possible eruption 60 years before the supernova. Could we be dealing with something entirely new? In this era of sky-scanning telescopes such as the IPTF, Catalina Sky Survey, Zwicky Transient Survey, and the Large Synoptic Survey Telescope, it's only a matter of time before we find more sources like this one, or weirder still.